Swayam Prabha. Digital India. Educated India.
Welcome to the lecture today, and like I announced, we have an extra lecture tomorrow at 11 and on Saturday at 11. Okay, that is to compensate for the 2 classes I am going to miss next week. Now, couple of questions were asked to me, and I thought what I will do is I will clarify those questions before I proceed further. The question is, in a vector space, is a basis unique or is the vector unique? So, let me explain whatever I wanted to tell you again. So, let us start with a very simple concrete example. Consider the vector space R2, okay. R2, basically what does this mean? The vectors have 2 elements, 2 coordinates. Each vector has 2 coordinates, and the dimension of this is 2. The dimension of this space is 2 because of this space is 2. What is the meaning of that? That is the maximum number of independent vectors I can have, okay. Dimension is 2 means this is the maximum number of independent vectors. If I take 3 vectors, it becomes dependent, okay. If we take 3 vectors, it will be dependent for sure. That is the meaning of dimension. Now, the 2 independent vectors, any 2 independent vectors can be a basis, okay. Basis is any 2 independent vectors. Basis is made of or consists of any 2 independent vectors. Supposing you are looking at Rn, you can just put instead of 2 put n, okay, but just to make it simple and clear, we are talking about R2. So, for example, 1 0 0 1 is a basis because these are independent, okay. Similarly, you can take 1 0 1 2, these are also independent. This is another basis, okay. So, the basis is not unique, you can have many bases. What do I mean by independent? If you do a linear combination C1 of this plus C2 times 1 2 equal to 0, how do I find out if it is dependent or independent, okay. This is what I am trying to do, to find out if dependent, we have to find this thing, that is our job, and this gives me 2 equations, C1 plus C2 equal to 0 and 2C2 equal to 0. So, the only solution to this is C2 equal to 0, and if C2 is 0, C1 has to be 0. Okay. This, the only solution is C1 equal to C2 equal to 0, therefore independent and a basis. So, basis is not unique. Unique means only one is possible. Basis is not unique. Okay. And if you look at 1 0 and 3 0, this is dependent. Okay. This is dependent. Why? Because this gives me C1 plus 3 C2 equal to 0. The second guy does not give me anything. Okay. C1 multiplied by this. So, basically how did I get this? This comes from C1 multiplied by 1 0 plus C2 multiplied by 3 0. Second guy does not give me any equation because 0 equals 0. So, now I can choose C1 and C2 to be non-zero, which satisfies, I can choose one of them, I find the other. So, if I choose C2 equal to 1, C1 is minus 3. So, there is a non-zero combination of C1, C2 possible, which satisfies this equation. Okay. And therefore, I say that is dependent. So, basically I can have many basis vectors. Basis is not unique. Now, but when you take but what is the meaning of basis? You can take another vector, an arbitrary vector, and write it as a linear combination of the basis. Okay, that is the meaning of basis. Okay. So, if you take an arbitrary vector, okay, and let us say the arbitrary vector x, which is x1 x2. So, basically x1 x2 is known to me. Okay. I can write this x, which is x1 x2, as C1 times whatever this basis is. I mean, let us take this one, C1 times 1 0 plus C2 times 1 and 2. Okay. I can take any arbitrary vector in R2 and write it as the linear combination of this. And what is unique? For that particular basis, the coefficients C1 and C2 are unique. So, the coefficients C1, C2 are unique. Okay. That is, if you substitute some numbers for x1, x2 and you solve this equation, you will get only one solution, C1 equal to something, C2 equal to something. That is what I mean by unique. So, the representation of a vector in terms of a basis is unique. The basis itself is not unique. Okay. Because you have many different bases. Again, I think I was trying to prove last class that the set of eigenvectors is forms an independent set. Okay. I think there was a question at the end of the class. Let me just go through that and hopefully it will become more clear. okay, set of eigenvectors n eigenvectors for n by n A matrix with n distinct eigenvalues forms are independent. So, I said when I said distinct eigenvalues, what I mean is they are not going to be repeated. Each eigenvalue occurs only once, okay, and since that means the algebraic multiplicity is 1. So, for every eigenvalue I have one vector. So, I have n eigenvectors is guaranteed for me. There can be situations where n eigenvectors are not guaranteed. I just do not want to confuse you by talking about that now. Okay. So, let us say I have n eigenvalues which are completely distinct. Each eigenvalue has one eigenvector and therefore, I have n eigenvectors. My claim is that these eigenvectors are independent. Okay. So, like I was doing last time, the proof is by contradiction. Say U1, U2, UR are independent. That means what? The other eigenvectors from UR plus 1 to UN, okay, are dependent on this. Okay. This means are dependent on U1 to UR. Okay. I mean, see, I want to show that they are independent. So, I am assuming they are dependent. Dependent means the small group which is independent. So, I am saying the first R are independent. So, now I am that is what we did last time. So, basically this means UR plus 1 can be written as a linear combination of the UIs, I going from 1 through R, okay, because these form an independent set. And I did this in two ways. I did two things. I operated on this by A, the matrix A. I got A times UR plus 1 equals sigma I equal to 1 through R A Ci UI. And A UR plus 1 is because these are all eigenvectors. So, I said this is lambda R plus 1 UR plus 1 and this is sigma Ci lambda I UI. A UI is lambda I UI because it is an eigenvector, okay. And the other thing I did was I multiplied both this equation by lambda R plus 1 throughout, okay. So, lambda R plus 1 UR plus 1 equals sigma Ci lambda R plus 1 UI. Yeah. Now, I subtract these two, the lambda R plus 1 UR plus 1, again lambda R plus 1 UR, subtracting these two at 0 equals sigma Ci UI. And I think this is where I didn't complete my argument properly yesterday, which is why I am doing this again. So, basically the lambdas were distinct, okay. So, this is non-zero, okay, because lambda r plus 1 is different from lambda 1, lambda 2, lambda r. So, this is non-zero, and I said that this is, I said the ui from 1 to r are independent. If this forms an independent set, the only way this equation can be satisfied is if Ci's are 0, okay. Since okay, and this is what I didn't do. If Ci's are 0, you come back here, that means ur plus 1 is 0, because the Ci's are 0, okay. Ur plus 1, which is sigma but ur plus 1 is an eigenvector and it cannot be 0 by definition, okay. That's the contradiction, okay. This cannot be possible because ur plus 1 is an eigenvector, okay. Eigenvector has to be non-zero by definition. So, basically what does this mean? This means our assumption that only ur are independent is flawed, okay. The entire thing is an independent set, up to un is independent, okay. Hence ui I going from 1 through n form an independent set, okay. So, anyway, I mean, some of these arguments you have to think about it. I think most of you are getting restless because too much of this general talk going on. You want to know, are we really going to solve any problems in life, right? Yeah, she's saying yes. Yeah, so let's do that, and then if necessary we'll come back to some general stuff again, okay. So, we'll see how we're going to use all of this, okay. How do I use all this framework, all these theorems that I've established to solve some problems, okay. How can we use this to solve a x equals b, an equation of this form, okay. Now, see, everybody is happy, we are going to solve a real problem. To begin with, we will keep life simple, we will assume A is real symmetric, okay. Let us assume A equals A transpose, okay. So, what I am going to do is tell you what are the things which are known to me. A is known to me, the matrix is known, this B is known to me, and what I have to do is find x. X is also going to be in the form of a vector. Okay, x is going to be also a vector. So, and I just proved that the set of eigenvectors forms an independent set. Okay, and for an n by n matrix, if I have n distinct eigenvalues, I will have n independent eigenvectors. I can use that as a basis. Okay, so let us, and it turns out for this matrix which is self-adjoint, even if the eigenvalues are repeated, they are not distinct, you are always guaranteed n eigenvectors. Okay, so for self-adjoint system, we are guaranteed n eigenvectors. Okay, even if the lambdas are repeated. Okay. So, what this means is I can use these eigenvectors as a basis. Okay. So, we use the eigenvectors as a basis, which means I can represent any vector as a linear combination of this basis. So, B, I am going to write it as sigma beta I ui, I equals 1 through n, small n, capital N, I am not being very strict about it, small n. So, I have n eigenvectors and beta I are the coefficients, because B I am putting beta. Okay. So, basically how will I find the beta i's? We are going to discuss that. Crude way is you can have a system of n equations you can solve, and x is going to be written as I equals 1 through n Ci ui, because x is also in the same vector space. X is also, I do not know what x is, I have to find out what x is. Okay, but I am going to get some solution which is also going to be a vector. That vector also is going to be written in terms of the eigenvectors as a linear combination of the eigenvectors. Okay. So, that is what earlier we were talking about. I mean, these eigenvectors, these n eigenvectors form a basis. So, any arbitrary vector can be written as a linear combination of these bases. That is what we are saying. Okay. So, now what is our job? Our job is to find the Ci. We also have to make sure that this equation is satisfied, right. The Ci should be such that I get an x which satisfies this equation. Okay. I can put arbitrary Ci. So, basically I want A operating on Ci ui, I equals 1 through n, equals B is beta I ui, I going from 1 through n. This is x, Ax, and this is B. Okay. Because of the linear operator, I can take the A inside and I can write this as sigma I equals 1 through n Ci. What is A ui? Because it is an eigenvector, it is a lambda I ui. Equals sigma beta I ui. I can bring this beta to the left hand side and I can write this as sigma I equal to 1 through n Ci lambda I minus beta I ui equal to 0. Now, because the ui's are independent, because the ui's are my eigenvectors which are an independent set, the only way this equation can be satisfied is if these coefficients are 0, okay, because the ui's are an independent set, we only have the trivial relationship which is Ci lambda I minus beta I equals 0 for all I, which means Ci must be equal to beta I divided by lambda I. Okay, or x, the unknown vector, or x must be equal to sigma beta I divided by lambda I ui I equals 1 through n. Now, given a particular problem Ax equals b, given a matrix A, I can calculate the eigenvalues and I can calculate the eigenvectors. Lambda I can be found out, ui can be found out. And given a particular B, I can find the beta i's. Okay, I can write that known vector B in terms of the eigenvectors. Beta i's are the coefficient. I can find that also out. So everything on the right hand side is known, and I can use this to find x. Okay. So I promised you will solve a problem. So let's solve a problem. So I mean, we just whatever I've written here in terms of beta, c, and all that, I'm going to take a real example and I'm going to solve it. I want to solve these two equations now, but I want to solve it using my method. And by the way, in the exam you have to use my method. You use any other method, okay. So this is a system of linear equations which we have, and I want to write this in the form of a matrix operator, okay. And x is x1 x2 and A x equals b is what I am going to write this as 1 2 2 1 x1 x2 equals 8 and 7. Okay. So I have just rewritten the system of equations in terms of this matrix notation Ax equals b. So I want to so the reason I chose this A is because it is real symmetric. Okay, I want to calculate the eigenvalues and the eigenvectors for this particular matrix. I want you to do it because you are all experts in this now. I will also do it, and if I make a mistake, you have to correct me. Don't wait for me to make the mistake. Okay, so let's find the eigenvalues. A. So that I am going to put 1 minus lambda 2 2 1 minus lambda, the determinant of this equals 0. These are A minus lambda I equals 4. So lambda are what is it? Minus 1 and 3. Okay. So these are the two eigenvalues we get. So I am going to say lambda 1 is minus 1, lambda 2 is 3. The first eigenvalue lambda 1, you can take any one as 1, does not matter. Okay, lambda 1 is, I am just saying lambda 1 is minus 1, lambda 2 is 3, you can take ulta, the opposite. I want to find the corresponding eigenvectors. Okay. So I am going to substitute here, and for corresponding to lambda 1 equal to minus 1, I want to find out u1, the eigenvector. So lambda 1 is minus 1, I substitute here, I will get 2x1. What are my equations? So I have to substitute lambda equal to minus 1, minus of lambda, so it is become plus 1. So 2x1 plus 2x2 equal to 0, and I substitute here, I get 2x1 plus 2x2 equal to 0. Is this clear how I got this? I just substituted lambda equal to minus 1 here. So you see that I get two equations, both of them are identical. So they are basically dependent on each other, or the rank of this matrix is 1. They are not independent. Okay. And what this means is I actually have only one equation and two unknowns. Okay. So I can arbitrarily set one to some number and find the other. Okay. So let us, so we have only one equation in two unknowns. So put x2 equal to x1 equal to 1, then x2 equal to minus 1. Okay. What have I done? I put x1 equal to 1 and I got x2 equal to minus 1. So my eigenvector u1 is 1 minus 1. And the other eigenvalue lambda 2 is 3. For lambda 2 equal to 3, I have to find the eigenvector corresponding to that. Okay. So I have to put a minus lambda I x equal to 0. I have to solve this equation. So I have x1 is, I have basically, I mean a coefficient is 1 minus 3, then I have 2, I have 2 here and I have 1 minus 3 here, x1 x2 equal to 0. I am doing this a more systematic way. So basically you found the eigenvalues by putting the determinant equal to 0. The determinant equal to 0 tells you that x is going to be non-zero. Okay. And so we want to find out the solution for a minus lambda I x equal to 0, and we want a non-zero solution. A has 1 in the diagonal, lambda is 3, so minus 3, this 2 comes here, this 2 comes here, there is 1 already here and minus 3. Okay. So basically I have minus 2x1 plus 2x2 equal to 0, I have 2x1 minus 2x2 equal to 0. Okay. Again you see that both are the same equation, okay, just one is multiplied by minus 1. So, I do not have to independent, I have this basically number of unknowns is 2, number of independent equations is 1, lesser number of equations. So, I can arbitrarily put some number, assign some value for one coordinate, find the other coordinate. Okay. So, I am going to put x2 equal to 1, set x2 equal to 1, then x1 will also be equal to 1. So, my eigenvector corresponding to this problem is 1 1. So, my eigenvector u2 is 1 1. So, lambda 1 is minus 1, u1 is 1 minus 1, lambda 2 is 3 and u2 is 1 1. Now, because this matrix is self-adjoint, because this matrix is real symmetric, what is the property of the eigenvectors? They have to be orthogonal to each other. So, you can verify if they are indeed orthogonal to each other. Is the inner product of this with this 0? So, the two vectors are orthogonal to each other. That is what we said. Self-adjoint matrices will have orthogonal eigenvectors. Inner product of u1 with u2 is 0. Okay. If you did not have u1 inner product u2 equal to 0, then you have a problem. I mean, somewhere you goofed up. The other thing you realize is that I put 1 as my choice, you could have taken 2 as your choice and then found. Then you would have gotten 2 2 here. So, basically inner, but orthogonality is still there. You can put 5 5, 10 10, does not matter. Okay. I had to choose some arbitrary number, I chose 1 because my brain cannot think beyond 1. But if you can think 2 or 3 or 4, you can do that also. Okay. And but so eigenvectors are not uniquely determined. If 1 1 is an eigenvector, so is 10 10, so is 5 5. Okay. Similarly here, so I have got the eigenvalues and the eigenvectors. Now, what I have to do is represent my unknown b in terms of these eigenvectors. Okay, b is 8 7, which I am going to write as beta 1, which is u1 1 minus 1 plus beta 2 1 1. Okay, and I need to find these coefficients beta 1 and beta 2. Now, typically what you will say, I will solve 2 equations in 2 unknowns, but we are going to exploit the orthogonality property. That is the whole reason we did all of this. Okay, we are going to use the orthogonality property to find these coefficients beta. We said no, when you have orthogonal basis, you can find the coefficients by just taking the inner product. You do not have to solve system of n equations. I am illustrating it for a 2 by 2 case. Imagine if you have a 100 dimensional matrix. So, okay. So, now how do I find beta 1? 1 will be take the inner product with 1 minus 1. Okay. So, inner product of 8 7 with 1 minus 1 plus inner product of this with 1 minus 1 will be 0. Okay. Beta 1, let me do this thing properly. So, I am taking the inner product of this equation 1 minus 1 is beta 1 times inner product of 1 minus 1 with 1 minus 1. The other one is 0. When I take the inner product with beta 2, okay. So, this is 0 because of the orthogonality property, and what is this? 8 plus 7, 8 plus 8 minus 7, 1 equals 1 2. So, basically beta 1 is half. Okay. We need to look at beta 2 now. To find beta 2, I will take the inner product with 1 1. So, I have 8 7 inner product of 8 7 with 1 1 equals beta 1, what is it? U1 is 1 minus 1 . Okay. So, I am getting 15 here. This is 0 because of orthogonality, and I only have this. So, imagine if I have n 10, 20, 9 of them will be 0 or 19 will be 0, only 1 will contribute. Okay. So, I am able to find one coefficient at a time directly. So, beta 2 will be 15 by 2. Okay. So, now I need to find x, that is my job. So, what have I done? The given B vector, I have written it in terms of my eigenvectors which form a basis, which are independent, which form a basis. I found the coefficients beta 1, beta 2. Okay. So, what we have done is x equals b, I found eigenvalues, eigenvectors. I am using this eigenvectors as a basis. I get b in terms of my basis, okay, which means I am finding the coefficients beta 1, beta 2, which is what I have done. So, now what is x? I mean, we did this great derivation earlier. I do not think I need this. X is, what are the formula we had? X is sigma beta I by lambda I ui, and boy, so it is beta 1 by lambda 1. What is beta 1, man? I erased it, half, is it? Half lambda 1 was minus 1 and u1 is 1 minus 1, okay, and beta 2 is 15 by 2 multiplied by there will be lambda, lambda, what is lambda? 3, yeah, thank you, and then I have 1 1. So, this is 5 by 2, okay, 5 by 2 and minus half. So, you can do this calculation, okay, 3 will go in this 5 times 5 by 2 minus half is 2, and I have 5 by 2 plus half, which is 3. So, basically x, which is x1, x2 is 2 3. Now, of course, you can go and substitute it back in this equation. X1 is 2, 2 plus 6 8, 4 plus 3 7, okay. So, this is basically, so it may appear to you, I mean, why are we doing this in such a, see, basically when you are writing a computer code for solving a large system of equations, the number of operations you do, okay, basically adds to the time for running the code. And so, basically you want to write an as efficient a code as possible. So, if you do the usual method of elimination or Gauss-Seidel, Gauss-Jordan, you look at the number of operations you have to do. I mean, you have solved these problems, linear equations numerically using different techniques, Gaussian, Gauss-Jordan, Gauss-Seidel. So, the mathematical operations required are quite high, number of operations. All I am saying is this is a much more efficient way, especially when your system of equations is large, okay. Of course, for a 2 by 2 system you do not have to do all this, but imagine you have a larger system, a distillation column with of trays, lot of species, then this method becomes more efficient. Okay, that is one thing. I think somebody asked me why are we doing this using the eigen values. So, now you see, because the ui's are the eigen values, when I write ax, I get lambda I ui. What you have been doing, so his I do not know who it was, somebody asked me, we already have a orthogonal basis 1 0 0 0 1 0. So, when you are solving your method, your thing using whatever method, when you represent x in terms of this thing, okay, so standard basis, that is what you have been doing all along, but you cannot, you know, exploit this thing. So, so here, since the ui's are eigenvectors, we can write a ui as lambda I ui and get the ci's. Okay. If they are not the eigenvector, if you do not use the eigenvectors, but if you use the standard orthogonal basis, I do not want this ui's are orthogonal because of a self-adjoint matrix. Okay. But if we use 1 0 0 1 as an orthogonal basis, then a times 1 0 may not be some lambda times 1 0. 1 0 may not be an eigenvector, that is what I am saying. So, then you can't do this, 1 0 may not be an eigenvector for A, 0 1 may not be an eigenvector, then you can't write what I did, A ui is lambda I ui. Okay. So, then if, so although one 0 0 1 are orthogonal, A times 1 0 is not equal to lambda 1 times 1 0, because 1 0 is not an eigenvector, as 1 0 may not be an eigenvector. I have used that, I have used A ui equal to lambda I ui. Okay. So, basically 1 0 is an eigenvector, no issue, I am using eigenvectors anyway. But so, if you take 1 0 0 1 which is an orthogonal basis, then because they may not be eigenvectors, you will not be able to use this approach, that is the first thing. And what you have done all along in your courses is use this 1 0 0 1. If I take x1 x2, what is x1 x2? x1 x2 are the coordinates, it is x1 times 1 0 plus x2 times 0 1. Okay. So, basically x1 x2 is x1 times 1 0 x2 times 0 1, correct. So, when you write x1 x2, these coordinates x1 x2 represent the coefficients in 0 1 1 0, and that is what you are working with. What we are doing is representing everything in terms of eigenvectors. So, think about it. So I will stop here.